This last section is about precipitation of salt. So we talked a little bit about precipitation before. If you're trying to figure out how much solid you're going to make or how much stuff is going to be left in afterwards, you have to do a BCA table and then an ice table to figure out what those ions are that are still in solution. But what we're going to do is figure out now if a salt will precipitate. So if you don't add in enough to make sure that it precipitates, then it won't, right? Some things are more soluble than others. So this is how we're going to do this. We're actually going to compare Q to K, just like we did in a previous unit. Anytime Q is not K, that means it has to shift one way or the other to get to equilibrium. And equilibrium is when it is essentially saturated, right? So KSP at equilibrium means that it's saturated. So what we're going to do is calculate Q. If Q is greater than K, that means it's got too many products. That means it's going to go back to the left. And if we're talking about a precipitation reaction, right, if it's AB makes A plus and B minus, this was our solid, and these are our aqueuses. Okay, if Q is too big, that means that I have too many products. So it's going to go to the left, which means it's going to make a solid. So if Q is greater than K, then a precipitate, which I will abbreviate as PPT, will form. Of course, in the opposite, if Q is less than K, that means that the Q value is too small. It needs to shift to the right to make more products. So that means it will become more soluble. So there will be no precipitate. Okay, it will be completely soluble. If Q equals K, then that means we're at equilibrium, right, at EQ. And for a solution with dissolving or solubility, that means it is saturated. Okay, if you add more in, it would precipitate, but you're right at the saturation level. Okay, so in a reminder, because when we are adding these solutions together to figure out if they were going to precipitate or not, you always have to account for a dilution, right? If I'm adding 10 milliliters of this and 10 milliliters of this, my new volume is 20 milliliters. So always keep that in mind. These concentrations have to be the new molarities. Okay, so if you're going to do that, then make sure that you use an M1V1 equals M2V2, or a lot of the times you can do it in your head, right? If you add 10 milliliters of this and 10 milliliters of this, then you're just going to half the concentration. But if you're not sure, do an M1V1 equals M2V2 to get those concentrations to use for Q or ice table or whatever it may be. Okay, so example number 8 says the solution is 0.05 molar of lead 2 plus and 0.025 molar of Cl minus. Okay, so I have twice as much lead as I have chloride. Does a precipitate form? Okay, so if I'm asking this, that means I need to calculate Q. All right, is it going to create a solid or not? The KSP for PbCl2 is 1.17 times 10 to the negative fifth. All right, so if I'm wondering if a precipitate forms, I'm going to calculate Q, and Q is going to be products, just products, right? Because reactants are solid. So I'm going to write the equation so you know what I'm referring to. PbCl2 solid breaks down into Pb2 plus and 2Cl minus, right? These are my aqueous guys. Okay, so Q is going to be the concentration of Pb2 plus times the concentration of Cl minus squared. Don't forget that squared, that will affect your results, okay? So I need to plug in both of these concentrations, and then I can solve. Now, remember, if I had given you like things you were adding together, you need to dilute. In this case, I already told you what the concentrations were. I didn't like dilute anything. So we're just going to plug these in. So if I calculate Q, right here, I'm going to put in 0.050. I'm going to put in 0.025. That one is squared. So I get a Q value of 3.13 times 10 to the negative fifth. Okay. Well, that compared to 1.17 times 10 to the negative fifth, Q is greater than K. So in that case, a precipitate will form. Okay. So that's all you have to do. Calculate Q and compare the two. Right now, we're gonna make it a little bit more complicated because usually we don't actually just add in ions, we put concentrations of two things together. So we're gonna have to look at that dilution here. Okay, so in example number 9, it says, will a precipitate form when I have 50 milliliters of this molarity, NaBr, and I put in 25 milliliters of this molarity, lead nitrate. The KSP for PbBr2 is 4.67 times 10 to the negative 6. Now, I recommend trying this on your own. But if you're not sure where to start because there's too many numbers, I'll walk through it with you. So if you're going to try it on your own, pause here. Okay, but I am going to walk through it now. All right. So let's see. We have, oh, my pen is not working. There we go. Okay, so we have 50 milliliters of this, 25 milliliters of this, and I've got KSP. So this is for PBBR2. So I'm going to go ahead and write out of that equation so I know what I'm dealing with. PB2 plus and 2BR minus, right? So I need to calculate Q because I'm asking, will a precipitate form? So Q is going to be the lead concentration times the bromine concentration or bromide concentration squared. So I need the concentrations of these two. Now, again, I'm adding, in this case, 50 milliliters to 25 milliliters. So I am going to have a dilution here. So I need to actually find these concentrations first. That should be a P. I kind of combined everything here, didn't I? All right, so let's do PB2 plus its concentration. Well, okay, so the lead is coming from this one. Okay, so I'm going to do an M1V1 equals M2V2. Well, it started at 9.0 times 10 to the negative second. That's my molarity 1. And I use 25 milliliters of that equals M2 times my new volume is 75 milliliters, okay? So M2 in this case ends up being 0.03 molar. That's a 3. There we go. Okay, same thing for my bromide ion. Okay, bromine came from the sodium bromide. So its concentration, sorry, my pen keeps glitching out. All right, this was 7.5 times 10 to the negative third molar, and I used 50 milliliters of this equals M2 times 75 milliliters. Okay, so the molarity of my bromide ion is 0.005. Okay, so we're going to plug those into Q, solve for Q, and see if we'll make a precipitate. Okay, so again, don't forget the dilution. So Q is going to be 0.3 times 0.005 squared. Oh, actually, that's 0.03. That disappeared. 0.03. So Q in this case is 7.5 times 10 to the negative 7. Okay, so we're going to compare this value to this value. Well, this is bigger, times 10 to the negative 6 is bigger. So Q is less than K, so there will be no precipitate. Okay, so adding them together, check your Q versus your K. Now, we can also use this information to selectively precipitate ions. And what I mean by that is we can add something in to actually try to get a precipitate so that we can take a solid out of something. So selective precipitation of ions is based on this same calculation. Okay. And what we're going to do is we're going to look at different K values to see if we can get one thing to precipitate, like without precipitating the other thing. That's selective precipitation. So for example, I've got barium chromate, its KSP, and strontium chromate and its KSP. And if you look at this, okay, this one is going to be much more soluble because it has a larger K value than this one. This one is less soluble. So what that means is no matter what I'm doing, this one is less soluble. So that means it will precipitate first. Okay, that means it's going to turn into solid instead of staying in solution. Okay, so as K2CrO4 is added dropwise, which will precipitate first. So that means like I have a solution of, I'm going to draw what the solution looks like. Okay, I have a solution of barium and strontium to begin with. I'm going to add this dropwise. Okay, if you start adding that in, eventually barium chromates, CrO4, will precipitate first. Because it has a lower KSP, it is less soluble. Okay, so the answer to that question is that barium chromate will precipitate first. Now, how effective would this separation be? Okay, what that means is like how much barium chromate can I get out before this also starts precipitating? Okay, which is kind of hard to tell when you're just looking at those KSPs. Okay, so if I want to know how effective it would be, essentially what you want to do is calculate the concentration of CrO4 2 minus needed for each. Okay, so like if I need to precipitate both of them. So the concentration to precipitate this one, concentration to precipitate this one. And if they're really far apart, that means I can probably get out most of the barium chromate before strontium starts precipitating. Okay. Essentially, what we need to do is keep the concentration below whatever the barium chromate needs. If it's really small, it's hard to control. Okay, so it is effective if the chromate concentration needed are, I'm going to put like in quotes, far apart. Like if it's something that we can actually precipitate out. Okay, so we're actually going to look at this solution. Example number 10 is this solution. I've got barium and strontium in here, and I want to separate it by adding potassium chromate. Now notice I'm just focusing on the chromate. Potassium is always soluble no matter what. So it's just really because you can't add a single ion. It has to be in a compound. So the KSP for barium chromate is this. I gave you this earlier. And for strontium chromate is this. Calculate the amount of potassium chromate needed to begin precipitation of both ions. So essentially we need to calculate what Q or K is going to be to precipitate. So wherever that saturation line is, okay? Then we need to calculate the amount of barium that would still be in solution when strontium starts to precipitate. All right, so like, can I get the barium out before the strontium starts to precipitate? That's the whole like, is this effective thing? Okay, so we're gonna look at both ions individually first, okay? So precipitating this and what concentration I need. And then over here, I'm gonna do the strontium and what concentration I need. So essentially, right, if I write KSP for these, now I'm not gonna write the whole precipitation equation. This is just one ion and one ion. So it's going to be barium concentration times the chromate concentration. Right. This one, KSP over here, would be the strontium concentration times the chromate concentration. Okay, now we have these because that was already in the solution. These are up here, right? 0.1 for this one and 0.1 for this one. I just want to know how much chromate I need to get to KSP. Remember, we're looking for saturated, okay, which is K. We're looking for when this is saturated. So I'm just going to set these equal to their KSPs, and it is really that simple. So this is going to be 1.2 times 10 to the negative 10th equals, this one I have in a 0.1 molar solution, and I'm trying to find whatever this concentration is going to be. This is my goal, okay? Over here, this one is 3.5 times 10 to the negative 5th. Equals the strontium is also 0.10, and I want to know this concentration. So I'm going to put X right here. Okay, try to find this. So I'm going to solve X for both of these, which is super simple. This one is 1.2 times 10 to the negative 9th molar chromate. That's what I need to precipitate that one. And over here, this one is 3.5 times 10 to the negative 4th molar of the chromate. That's what I need to precipitate this one. Okay. So essentially what this is then getting at says when the concentration needed to precipitate both. So this is like one answer, right? For this one, this is an answer for this one. Okay. Now notice these are very, very small concentrations, 3.5 times 10 to the negative 4th and 1.2 times 10 to the negative 9th. Okay. So essentially, this is going to precipitate really easily, but this is also really low in concentration. So we're not going to be able to get much of the barium. Okay. Again. So to actually calculate this and prove it, we're going to calculate how much barium would still be in here when this starts to precipitate out, like when I hit this one. Okay, so this will kind of prove to us if it's going to be efficient or if it's not. So how do I calculate that? Well, I want to know how much barium, right, is left essentially when I hit this concentration. Okay, so I want to know this guy. Okay, so what I'm going to do is I'm actually going to plug this concentration of chromate in for this equation over here. So the barium chromate. So it would be like, okay, well, 1.2 times 10 to the negative 10th, that was my KSP, equals, barium was still at, no, I want to know the barium concentration, sorry. I wrote that incorrectly. Right, oh, shoot. We want to know what the barium concentration is still going to be. So we go this guy, what is the barium concentration when chromate is this 3.5 times 10 to the negative 4? Okay, so if that's the case, when I've hit that concentration, my barium is 3.4 times 10 to the negative 7th molar. So this would be when I precipitate both. Okay, so it went from 0.1 to this, which in this case is not bad. Okay, so the barium would be, this is much lower than 0.1 molar. So that means I actually would have precipitated quite a bit of it. So it's good. Now, if this had been a high concentration, maybe it was like 0.09 or 0.08 or something, then I actually didn't get much out before the chromate started to precipitate. Okay, so essentially what we did, we calculated how much chromate I needed for both, and then how much barium would be left when I started precipitating the chromate, like when I hit this one. And since this is low, it's actually a pretty effective separation method. Now, like I said, if this had been a lot bigger or closer to what it started with, then it is not a very effective separation method.